Yeah, we are live now. So, Mike, very, very warm welcome to you on the Semiconductor Podcast. So, this is the third episode, and great to have you here in this
Thank you, Murdo.
podcast.
Appreciate the interest.
Yeah. So, the community here is mostly the students and semiconductor enthusiasts who are encircling around different domains of VLSI. So, my first question or and kind of it will be your introduction too. So please tell us about your journey and stopover points in your career. So you may
Okay,
uh, go in the fashion that you like, so that
great.
people will know about you.
All right. My background is experimental physics. Uh, I've actually never had an engineering course in my life. My role there was electronic design. I designed the electronics for physics experiments that couldn't be purchased off the shelf, and I went into simulation fairly early, and it was a, a parallel interest in that effort. I stumbled into SPICE in a very disorganized way. My first simulators were for analyzing nuclear collision in a particle accelerator, and then later for charged particle optics. Notably, I designed a couple of objective lenses for scanning electron microscopes. The success of the optics simulator was due to the way it integrated relativistic kinematic equations. I was able to analytically remove 1 degree of freedom, which gave a fantastic improvement in the accuracy and allowed aberration coefficients to be readily predicted. The next big simulator I wrote was for identifying hydrocarbon bearing strata miles below the Earth's surface, like, oil exploration. I was an oil
Yeah,
prospector.
yeah,
And people like to criticize the oil industry. That's all fine. But if it weren't for fossil fuels, whales would be extinct. Kerosene replaced whale oil for lighting our homes and streets. Okay. Anyway, in that, in my bout with oil exploration, that's when I started designing analog electronics, and how I got into SPICE. I was designing circuits with a service temperature, that where they were intended to be operated at 200 C. And for that, I had to make my own semiconductor models. And that led me to think that I was pretty much at the forefront of understanding SPICE. SPICE was, in fact, a component in the simulator I had written for identifying hydrocarbon bearing strata. Anyway, that answers my path.
yeah. And then about around the LT spice and then something
Okay, well,
for
as far as SPICE itself, so that was the first answer was about me, and then as far as SPICE,
yeah,
SPICE started out as a class project at the Berkeley campus of the University of California, University of California in 1968. At that time, it wasn't called SPICE; it was called Cancer, which stood for
okay,
Computer Analysis of Nonlinear Circuits Excluding Radiation. And I spent years thinking that that name for meant excluding radiation meant electromagnetic radiation because, SPICE was a lumped constant solver, which almost automatically excludes far field effects, and electromagnetic
yeah,
radiation. But that's not what they actually meant when they thought up that name. They meant particle radiation, like from a nuclear weapon.
yeah,
And the point of the name was a nod to the anti war movement at Berkeley in the 1960s, and it made sense to them at the time. Okay. Now, the dean, the UC Berkeley dean, found cancer unacceptable, and he required that a nice name be found for this software engineering project. Well, that's where they contrived the name Simulation Program with Integrated Circuit Emphasis, SPICE. And it was another in your face name. I mean, if you insist on a nice name, what could be nicer than SPICE?
yeah, yeah, yeah,
But the interesting thing about SPICE is that it seems to be doing the impossible, solving the general nonlinear system. I mean, we've all had university courses on linear algebra and learned about
yeah,
matrix
yeah.
rank and order and eigenvalues and determinants, and most importantly, how to solve them. But the
Yes,
last day of class, the professor turned around from the chalkboard and looks at you and tells you, this is how you solve any linear system. If you have a nonlinear system, we're going to wish you a lot of luck with that, okay? because
True.
there is, solving the nonlinear system is pretty much exactly what is impossible. But then there's SPICE. You give it some random nonlinear circuit, and it effortlessly solves the thing. Well, what's happening is that it's not solving the general nonlinear system. It's solving a very special one, and that is specifically one where all the IV curves are continuous in both value and slope, and that allows the solution to be found with Newton iteration. The thing about Newton iteration is that it looks at your nonlinear system and says, look, I can't solve this, but I can approximate it. And I'll approximate it as a Taylor series, but it's a multi-dimensional Taylor series.
Yes.
You say, and I'll approximate it just to first order. So you guess some solution, say everything is 0, and I'll evaluate I'll evaluate every IV curve at that guess solution, keeping the 0 order term and the first order term. So I approximate it, to first order, and then now I have my approximation is linear, and I'll solve where it is actually biased. And then it turns out that if the solution of a linear system is the point about which you expanded it, well, that's the answer, and you've proved it, because your approximation is not an approximation at that point. It's exact. And Newton iteration results in a numerical proof it's found the answer. Now, the other thing about Newton iteration is that it's exceedingly fast. It's basically the FET of error minimization. If you're within 1% of the answer, your error, you expand to first order, your error is second order. So if you solve it once, you're not within 10 to the minus 2, you're within 10 to the minus 4. If you do one more Newton iteration, you're within 10 to the minus 8. And if you care to, you can do a third Newton iteration, be within 10 to the minus 16. You can't even store answers that accurately. So basically, it's solving the nonlinear system at the cost of being 3 times slower at solving the linear system. There's a crude way of speaking. So it's blindingly fast. It effortlessly solves nonlinear systems. Now, there's actually 3 numerical methods that create a perfect storm in SPICE that make it just wildly useful and makes it even, 50 years later, still the way you solve analog circuits. Another method is sparse matrix methods, because, when we learned in school, we were all thinking about dense matrices. Well, circuits are not dense matrices. Even if you have a schematic that looks like a fishnet of resistors, if you make a matrix of that, you don't have any if you think of the conductivity matrix, you have the diagonal, and then you just have non-zero elements, one axis off, one IJ off of diagonal, because you only have adjacent conductivities. You don't have adjacent from this resistor to every single other resistor in the matrix. So it's an exceedingly sparse matrix. You only have to do a few floating point operations to eliminate each unknown. So you can solve. So by using sparse matrix methods, you do 2 things. One is you get a fantastic speed increase. You reduce the memory requirements by a factor of 1,000,000, and it's more accurate because you have so many less floating point operations you do, and it's so much faster. So matrix methods. And then the third numerical method that's important to SPICE is using something called implicit integration of the differential equations that arise from the reactances in the circuit. And there's an interesting thing here, an interaction between academia and actually trying to solve something in simulation. So, you've probably had courses in how to integrate differential equations. And, the example is always a cannonball,
Yes.
And if the cannonball is at this point in this direction at that speed, then the next time step it's here, but there's been a force, so now it's going in a different direction at a different speed, and you keep integrating that step by step by step, and that's how you solve the solution of the cannonball. And it works great for cannonballs. But you get out in the real world, it can't solve any circuits at all, because, except for planetary motion, you don't have, the solution doesn't look like some ellipse. The solution is usually some decay. For anything here on Earth, it's all decaying exponentials, whether it's a thermal or an RC circuit or anything. Everything is decaying exponential. And if you have a system where the solution of the integration of the differential equations is decaying exponential, your errors exponentially increase time step to time step. And if you try to use these explicit methods of integrating the differential equations, your numerically integrated result just runs off to infinity each and every single time. You can't solve your circuit.
Yes.
It's very
Yeah.
frustrating.
Yeah. Yeah.
I've
Yeah. Yeah.
enjoyed that frustration multiple times in my career,
Yes.
learning how to do
Yes.
these. Anyway,
That becomes a sort of challenge at that point, I guess.
yeah. Anyway, so that's the thing about SPICE. Okay, that's its history, and those three numerical methods are what makes SPICE. It's just a perfect storm of that's why SPICE is just took over the electronic design community. Okay,
Yeah. And
I
yeah, here I would like to have interruption to your uh,
oh
answers and all. So yeah, and one thing, when the SPICE started, right, that time all together there were theory of physics, electronic circuitry, circuit theory, network theorems, everything was around, and it was merged into probably C++ code for a SPICE, I guess, like that. So how that amalgamation happened around you when you was there, like that thing? Because when people see about softwares, they think of C++. When they think of textbook, they think of, okay, we are going in the network theorem and all that, KCL, KVL, and all those stuffs, right? So it's a very simple question from my side, that when a students look onto them, they are different subject, but when in real world we have a simulator, everything is integrated, everything is working hand in hand through code. So how that kind of amalgamation you faced, and what was your experience that time?
um I have to confess I'm not sure if I understand things. I'll I can always go into talk about details. Let's go with details and see if I get any
Yeah,
traction on
sure,
your
sure, sure,
question.
sure,
Okay,
sure,
good.
sure.
So
I'm looking for
Spice
that.
was originally written in Fortran, and the last Fortran Spice was version 2G6. Spice 3 was moving away from Fortran to C. And it's strictly C. It's K and RC. It won't compile in a modern compiler. Uh, and it remains in C, K and RC, which is this awful language. For a student, you should always write in at least C++ quality C code. Even if you don't want, if you want to stick to 22 keywords of C, that's okay. But make sure that you're using function prototypes and a full-on ANSI C, because that it is much less error prone than coding in C. Okay, so with Spice 3, it went to C, and it got in some ways harder to understand because, okay, so it went to C in the 70s, and they thought that it was they tried to make it object-oriented programming before object-oriented programming became a buzzword in trade journals. Okay. And so when you look at this code, even if you've had the benefit of someone from the original Berkeley CAD group. Now, I am not from the original Berkeley CAD group. That was Evans Hall, and I was in LeConte Hall at Berkeley. Okay, so they were,
Okay.
there's a big sidewalk between the two, and we didn't talk to each other. Okay,
Okay.
but
Okay.
I have had the benefit of having someone from the original Berkeley CAD group explain SPICE, how it works, what the numerical methods are, and almost most importantly, why it is written the way it is. Because if you look at this code, it's just C code, and it is extremely obtuse. And what they were doing is they were trying to do object-oriented programming from a methodology that died in the 70s. So if you look at it in the 80s or 90s or noughts, it does not make sense what they were doing. It's just, you figure I'm gonna work on something else. Okay, it's just not good. So that's okay. So I delved into detail because I'm not sure I understood your question. Now you did talk about the way it appears to. Oh, I did answer your question.
Yeah, I am happy. Happy because that is how actually people see different subjects at different subjects, and they want to clear their exams. But in real world, when everything is amalgamated, I asked that, and you said that everything, how it made its journey. Now I, from that point, I'll move on to my next question. In early days, how the SPICE was, and it has gone through multiple mutation, multiple branches, proprietary spices and all. In your vision, how the journey path of yours, how did you see spice evolve and from a smaller capability to higher capability? So if you share what your experience around the spice.
Um, so I think um, I think that okay. I think that spice has been developed best by the people that got into spice modeling. Um, the spice source code itself. Okay, by the 1990s, the dean of UC Berkeley says we're not going to write spice anymore. We're not a software company. We're an education institution. It's what made sense to him at the time. So, the spice source code tree is mostly at the end of its development. Okay. Now, you can take that source code tree and be like me and write tools that will convert it into something that will compile in a modern compiler, get it towards ANSI C++. But if you really want to make real developments and real improvements in the simulator, you have to be involved in modeling. You have to make device models not only of semiconductors, but the other things that you want to put in your SPICE simulation. I mean, a good example of this is the example of the Haley twins working on HSPICE. They didn't want to work on software; they wanted to make models. And then it's the more models they would make for semiconductor manufacturers as a contractor, they wanted them to develop the SPICE improve the SPICE code itself. So they did that. And that's how HSPICE came. It came as a result of modeling. And I have a similar path there, and that I benefit from having started, maybe 20 years after the Haley brothers. So there's a lot of what they did that isn't used anymore. I don't need a level 28 MOSFET. It's not.
Yeah.
So I don't need to go through the work of implementing that. So I, and also I benefit from the fact that computer science has improved since HSPICE was written. Okay, I use methods like in the waveform viewer, I will replace data with procedure, so it takes less space on the disk. I won't put the current in a resistor in the waveform file. I will write an expression how to compute that current as the voltage between these two nodes multiplied times the conductivity. I'll put that as an equation inside the header file, and that's a fairly advanced database technique of replacing data with procedure, because procedure is just a paragraph and data is gigabytes, and that helps a lot. So I have the benefit of more modern computer science. It helps somewhat to have more modern compiler theory, because there are compilers compiler technologies used extensively in SPICE simulation, and I just have better software tools. I mean, today I think you can download a tool like Microsoft Visual Studio and use it for free. And I remember when a tool like that would cost $50,000 to run on a Sun workstation. I mean, you got really good software development tools today. Anyone can do it. I might have lost the thread of your question.
Yeah. So I asked about the evolution of spice. That means
Okay.
from early days, how it changed itself, mutated, and become more advanced.
Okay, so SPICE itself got more and more device equations for more and more different types of MOSFETs. Subthreshold conduction was added. For the very short channel devices, all these different tunneling currents are included. Basically you had to extend the device equations to model as dimensions got smaller. You had artifacts in the IV curves of the MOSFETs that you'd have to add. The charge models improved. The original Berkeley SPICE, well, this is kind of a strange story here, but the original Berkeley SPICE used something called the Meyer model, which was capacitance based. And it got a bad name because if you were trying to design a DRAM, because it didn't conserve charge, the gate voltage would go wander off to, some preposterous voltage, because it wasn't stipulating that charge had to be conserved. So you had various variations of the Yang-Chatterjee charge model. Chatterjee being a Texas Instruments fellow, and uh, and all that got cleaned up. Though for a lot of simulation, the Meyer is just fine, computationally lighter weight, and may give you less convergence problems. There's nothing wrong with the Meyer model for most analog circuit design. Um, I use both. And in QSPICE, or the most recent simulator I wrote, even for MOS level 1, you can use the Yang Chatterjee or you can use the Meyer model, which is, you know, um, uh, something that it's an idea I took from HSPICE. HSPICE will let you run Meyer BSIM1 charge model in the MOS. You can pick different charge models for the same device. So that's what I did in QSPICE. Is now the one big evolution here that I personally have worked on is that, or that that I take some responsibility for, is that I've added the ability to include massive amounts of digital logic in a SPICE simulation. Okay, so in QSPICE, you can spill over into Verilog, digital Verilog, or C++, and just code up what you want. And this stuff is QSPICE includes Verilog and C++ compilers that convert all of that to native Intel opcodes, and you just execute that object code during the simulation. So what happens is this phenomenal thing. QSPICE can simulate digital logic faster than the hardware.
Yeah.
Unless you're simulating some Intel CPU, then it computes at the same speed.
Okay. So here I'll take another question that you talked about QSPICE, right? In we will come to QSPICE later. Previous to that, I think. Uh, can you share some memory lane experience with LT-SPICE?
Well, okay, so LT-SPICE was interesting for a few reasons. I joined Linear Technology Corporation to fund writing LT-SPICE, and elsewhere I have this article that explains the whole business side of that in some detail. It's a real tell-all, but it's too lengthy for our purposes here. Okay,
Yeah.
so most briefly on that topic is the odd thing is nobody wanted LT-SPICE. They just didn't want it. Okay, Linear Technology Corporation, which was a great company. Linear Technology Corporation, blamelessly wanted the same sort of sales collateral software that other semiconductor manufacturers were developing. Some spreadsheet-based selection guide that would corral what a customer wanted into something that they could be sold. Okay, that's what everybody else was doing. It would be natural to just want to do that for your products too. Okay, but I had a very, very different agenda. And my agenda was to distribute a free, uncrippled SPICE program. And I was pretty sure I could write a better SPICE program than the other stuff that application engineers were using. I mean, my focus on this is all board level design, to be humble
Yeah.
here. Okay,
Yeah.
it wasn't okay. And the idea of distributing a free, uncoupled SPICE program was not a popular idea. It just seemed like a really bad idea by my peers. But the idea, to do that won out basically because I rather bluntly insisted that we do that. Okay. And
Okay.
LT-SPICE was great because well, for one thing, it demonstrated that you actually, from a business point of view, you could make a lot more money by giving software away than by selling it. Okay, because you would give LT-SPICE away so that engineers would develop their intuition in how to use a circuit, and you had models for all the linear tech parts. Those products became part of the engineer's intuition, and so those are the parts that would fill the sockets. Okay, and it was
Okay.
really, really successful. And so LT-SPICE started out. Linear Technology was selling about 400 million in ICs a year, and by the time I was done with it, they were selling $2 billion a year in ICs.
Okay.
So it was, it was a very successful engineering project. And, with LT-SPICE, I lived a wonderful life, after having written it. It actually, the LT-SPICE, the original version of LT-SPICE only took 10 months to write. Okay. For, schematic capture, SPICE program, waveform viewer, cross probing, an up to date for 1999 graphical user interface. Took about 10 months to write. And so in the 19 years I was with Linear Tech, I was mostly on perpetual lecture tour. I was on a different continent almost every month giving seminars, which for me was mostly just for the fun of it. I mean, yeah, I would get, everybody wanted to have an LT-SPICE seminar, so I would just pick where I'd go because everybody wanted one. And when I did come into the office, it was just to logisticize my travels, and I'd pore over Google Earth to find interesting new places to go. Okay.
Okay.
I ended up lecturing in 48 countries, and I've been to India many times. Which was
Great.
that had influence on me as a human being, because the first time a Californian goes to India, it's kind of scary. Okay, just it is.
Okay.
It's not what people expect, and it's very different. But by the fifth time I was there, I got to the point where I could navigate and cross the street by myself. And I was comfortable making eye contact to others to communicate my intent and my path through the traffic. I was able to do that. And I frankly felt like I had become a better human being from that experience.
Great to hear that. And your travel across 48 countries during that, it also had a face-to-face and heart-to-heart contact with many of the enthusiasts, right? So that, I think, poured a lot of energy into you. This is my guess. Maybe yours experience you can share.
I very much enjoyed that whole experience, and I recall experiences where, like, I remember this was in India. I was talking about Bodhi plots and stability analysis, and I had a very young engineer who hadn't heard of Bodhi plots before, didn't know what it was about, and I explained it, and just to see a person revel in the beauty of them I still remember to this day, because I remember myself back in the the 1970s. Somebody explained to me, I was working on the circuit, and this coworker, a graduate research assistant, told me, look, Mike, if you're going to use negative feedback, make sure that the feedback drops below unity gain before you acquire too much phase shift that it's going to oscillate instead of being stable. And I remember that moment. It was like I fell to my knees and took a solemn oath I would do a Bodhi analysis of every single circuit I ever sold to an employer ever. I outgrew that point of view. I think there's, especially for nonlinear circuits and switchboard power supplies, I've evolved to the point where Bodhi analysis is not much more than a distraction, because it's easy to obfuscate what actually causes the circuit to be unstable if you go into that mode, because many switchboard power supplies are self-oscillating. You actually want them to oscillate, and Bodhi analysis becomes kind of not so useful. Plus, there's the whole thing that, you don't want the phase shift. Excuse me. You don't want the phase shift to. Excuse me.
Yeah, you can take some water.
Okay, so you don't want the phase shift to become too much before you go to 0 dB. But if you get a lot more phase shift, that's okay too. It's still stable. So it's kind of not such a direct method. You don't quite look at it's not quite as useful as it first comes across. But I remember telling people that and watching them metabolize this information on their feet, just like I had 40 years earlier. So that was an interesting experience.
Yeah. And that's the thing I was looking for, because now you are virtually connected to many people right now who are in live session. They are watching, so they are hearing you, and some people will later see the recorded version of this podcast, so people will also maybe doing some comments. I can send it to you.
Okay.
And yeah, so you were talking about QSPICE. So from your some initial details of the QSPICE, I understand that nowadays in VLSI we are looking for the mixed mode analysis like Verilog and Spice, uh, mixed mode simulation. So QSPICE, in that context, can you elaborate a bit what QSPICE does, who are the intended audience, like that? So
Well, for okay, so there's different approaches to mixed mode simulation, and one of them is Verilog-AMS. Another would be, there's various mixed mode simulation capabilities. I'm trying to do better than all of that in QSPICE. And it's a two-pronged. So on the analog, I just want to have a better SPICE program. I've spent decades working on it. I've flung my metabolism at it for so many years. I think I have a better SPICE program on just SPICE basics, okay? But on the digital side, I I want to be able to present horrific amounts of digital logic to an analog circuit. I'm not so interested in debugging your digital logic. Okay, so yes, I
yeah,
will
yeah,
simulate digital logic faster than typically faster than a commercial digital simulator. But I don't keep track of whether or not data is initialized or not. I'm just trying to present a large of data, not trying to help you design that digital data necessarily. Aside from the fact of the way it will impact the analog part of your circuit. So I want to use SPICE methods and actually hand-coded SPICE devices and not Verilog-A. Um, Verilog-A will let you write device equations, and I was hoping that would be useful. And I did some work in implementing and bringing. And I've run Verilog-A and QSPICE, but I'm kind of disappointed with the whole thing. I think that I would prefer to use hand-coded device equations because if you hand-code the device equations, a few things happen. One is that you can trap the numerical singularities that occur. And to solve those singularities, what you usually do, the most common thing you have to do is apply L'Hopital's rule. Okay, it's usually a
yeah, yeah,
mathematical
yeah,
artifact, not
yeah.
the transistor doesn't blow up with a singularity. It's the way you've presented the equation, so you need to reformulate them to avoid the singularity. It's just an artifact of your mathematical formulation, not the way the parts actually work. Though sometimes you do have to um, uh, add structure to the device equations to add non-physical eliminate non-physical behavior. One of those things would be the reverse recovery time of a diode. So
Mm,
when you in a diode, you have this parameter called TT, called the transit time. And yes, it has the dimensions of time because if you take the forward current and multiply it times TT, current times times is charge, and that tells you the amount of
mm,
charge
mm,
in the diode that you have to pull out of the diode to get it to turn off. Okay, so it's a coefficient with the dimensions of time. But in SPICE programs in general, from time, okay, so it's conducting like a wire until you pull out that charge, then it goes to open circuit. Okay, it acts like a perfect snap diode. And snap diodes are real things. You can, the fastest rise time you can get in electronics, to the best of my knowledge, is from a snap diode. You can make a pulse that goes to a few volts and back in, maybe 100 picoseconds using a snap diode and a differentiator. I used to do that in nuclear instrumentation, but which is my electronics background. But
yeah.
uh, most diodes don't snap off. Most of them rather take their time and rather slow ways to turn off. So yeah, that's a case where you actually change the device equations to be more physical, and that's what I've done on all the SPICE stuff. They're all hand coded SPICE devices. You avoid singularities, manifestly non-physical behavior, and also if your IV curves are extremely nonlinear, you can give hints to the rest of the solver on how to navigate that nonlinearity, and that you can do with hand-coded device equations. And I don't really see that happening in Verilog-A implementations. Uh,
Yeah.
so that's how I do with the SPICE. Now for the digital part, well, I have this way of handling the time step control of the digital and analog, which to my mind is kind of optimal. So I can just evaluate the digital stuff as object code and present that to the SPICE simulation. They don't get in a fight at all over time step. They got no trouble with it. So I think that I should be, my methodology is absolutely capable of outperforming any Verilog-AMS implementation. And then the question is whether or not I've coded it up to actually do that. But that's where I am in Verilog. I may eventually add Verilog-A to QSPICE because it would be nice to try to prototype device equations.
Yeah.
But that is something that not very many people really do. You know, I think I would probably use it more than most other people. I mean, I might be used in coursework, you know, but it's not something that happens in industry, you know, because QSPICE is really about who should use QSPICE is anyone who wants to buy or sell an integrated circuit should be using QSPICE because it's a lot easier to present the behavior of an integrated circuit with QSPICE to the rest of your circuit than it is in any other simulator. And that statement I feel completely comfortable with as a person who's modeled very many hundreds of ICs.
Yeah, and if I am not mistaken, so Verilog-AMS and Verilog-A, they were coming from the side of the Verilog system, Verilog, and all that family, right? So for the abstraction level of analog circuits, right? So they are more kind of in abstract level than detailing level is SPICE. So when we do the SPICE, it is more detailed and more accurate because Verilog-A or Verilog-AMS will create some abstract models and quicker simulation time, and that's how the abstract things will happen. But however, if we go down more in detail in the transistor level, there only we have to encounter SPICE, and nowadays circuits are having the Verilog and SPICE interactions in a chip. There will be some blocks are in Verilog, some blocks will be in SPICE. They have to interact and handshake among them. So that is the need of hour right now. What I feel, audience.
I think you're giving good advice there. I think you're giving a good perspective. That's certainly the legacy perspective. To a large extent, I'm trying to do the next thing above that perspective. Okay, I'm trying to let you have detailed SPICE, and I'm trying to give something that's even more abstract than Verilog-AMS. So I want to make it possible that you can have truly horrific amounts of digital logic and present that to an analog part and get full SPICE accuracy and get improved simulation speed from your digital. That's my goal. That's what I'm trying to accomplish in QSPICE. You know, I think I've got that. You know, really.
Yeah.
You know, I can. You know, when I make a model of a switchboard power supply, if you have to program it with SPI or I2C, you just clock at those pulses, and it just reads that, and you can do a startup transient analysis in a couple of seconds, and all that. You know, it's a literal model of the integrated circuit because of the methodology I'm using, and it is a level above. You know, I think it's the next thing above Verilog and Verilog-A and Verilog-AMS.
Yes. And one question here is that we talked about the Verilog, we talked about system Verilog. Just in last last interaction, I said now these languages like Verilog, system Verilog, Verilog-AMS, all those have some unified body like IEEE or Accelera. They are guiding and giving guidance so that it can become uniform. But throughout my career, or even before when I was in academics, I see that there are a lot of SPICEs around across different companies. Their language itineraries are also a bit shifted sometime. Not every time that HSPICE and Spectre and PSPICE, and they do have common philosophy inside. But however, the language is different. Why was not there any body like IEEE or Accelera looking into that so that the code can have some exchangeability or kind of that, or you can say it in a better way? That I was trying to explore the question even. So
okay. Well,
yeah.
I guess I have three comments. One is that the reason why they don't interoperate is because everybody wants to have a proprietary SPICE. You're tied into just
Okay.
using their SPICE program. That's, if you will,
Okay.
the
Yeah.
end. But aside from business models, there's two other comments that more technically answer what you're asking. One is that okay, so for decades there was a very high level of interoperability between SPICE dialects. Okay, you could pretty much take models from one and run it in another. Okay, and the reason why that it worked surprisingly well, even though everybody wanted to have their own proprietary version. The reason why is because they were all based on the Berkeley SPICE code. Because Berkeley SPICE was developed by public funds, the owner was the American taxpayer. Okay, it wasn't a company. And so you could obtain the source code to Berkeley SPICE by a small cost of the distribution, to make a tar tape, and sign in an oath to not share it with the Soviet Union, China, North Korea, and probably 20 other countries in the East Bloc. And I've signed that oath, and I've honored that oath. So you can get the Berkeley SPICE source code for about $50. Okay, so that was the first, say 20 years of SPICE, and then all these. Everybody who paid $50 tried to make it proprietary, so that you had to use their $50 version, which they'd sell you for $50,000. The old business. In the 1990s, this is the way it would work. You'd take the Berkeley SPICE code and you'd replace the Meyer model in the MOS level 1, 2, and 3, and with the Yang Chatterjee model from BSIM 1, and then you go around to all the semiconductor manufacturers and you say, "Now look at this. You run this simulation in your SPICE program, and you see this gate charge goes wandering off to where it can't. It's not conserving charge. That's important, But you run it in our SPICE program, and it conserves charge. And that's why you pay us $50,000 for the SPICE program, okay?
Nicely explained.
Huh? Yeah.
Nicely explained.
Okay, that's the way it worked. Yeah, guilty pleasures. Okay. However, there is another thing to comment I can make on this long. There is something called the Compact Model Coalition, and they try to release device equation amongst themselves and hope people use them. They have all these great ideas. There's all this literature, but they don't make it that much into PDKs. Everyone's using SPICE devices that were still written in native C code. Anyway, the Compact Model Coalition, what's good about them is that they understand that there aren't many people that can write native SPICE devices anymore. They don't have a pulse anymore. Okay, there's just not very many people. So looking for an alternate technology is entirely benevolent, and also the people who write it, they particularly were further away from the SPICE thing. So they would rather have everything in Verilog-A just to move away from Berkeley SPICE legacy, which they have not so much connection with. But, I'm still alive. I'm still writing native SPICE devices. And
Great.
and the
Great.
and the PDKs are not in those Verilog-A parts. They're in old-fashioned C code, native SPICE devices.
Great to hear all about the things you shared. And now I'll be moving to another question that with time, right? Do you have any kind of idea or roadmap to integrate Verilog-A, Verilog-AMS in QSPICE along with the Verilog, that thing you already shared?
Okay, so like I did say, Verilog-A is interesting to me in the interest of being able to rapidly prototype device equations. And I would like to rapidly prototype device equations not just for semiconductors, but for electric motors. Okay, that would be the value. That's actually that's where the value would be to me. And I did. Yes, I have run Verilog-A in QSPICE, and its internal framework is there, but I'm not I'm not that happy with it, and it's not going into release anytime real soon. So I don't know if that's at a roadmap or sidelined at the rest station, but I'm not working on that today. That's for sure. I got other problems I need to fix this afternoon. My afternoon. You'll be sleeping. Once you're sleeping, I'll be happy coding away.
Yeah, yeah, I like that. We are in the two farthest zone of the earth. Uh, so next question is that like it's because in our audience, right, they are from the VLSI background, either they are students or they are working, right? So one
Mm-hmm.
question here will be very much interesting. Like we have sometime PDKs from various foundries, right? Inside that we have some spice models or so. Like that we have a open kind of PDK from Google, right? The Skywater PDK, like so. Is there a roadmap of that kind of PDK integration into QSPICE, any in any manner, right? So for the
Okay, so
analog part.
this is something that I'm more interested in than implementing Verilog-A. Okay, I have run a few PDKs. Okay, and yes, I'd have to make little. I have to change little parsing aspects here and there, and I've run maybe three. Some were under NDA only, and I don't. I deal more with uh, uh, higher. I deal more with board level design than IC design, though I deal with IC designers all the time. So it's like this. Yes, I've run a few PDKs and I've made modifications to QSPICE to run them. And I fix any issues as they're presented to me. But quite frankly, if someone has to ask if they can run a PDK, I don't give them encouragement because there's going to be a lot of CAD details they're going to have to deal with. And it's not my focus right now. But it will eventually run PDKs. That was of interest. But if you have to ask, I would just say no. Just do other circuit design with QSPICE for now.
So in every corner of the world, the AI and ML is now buzzing. So is there any chances of AI or ML into the analog design or verification? How do you see it?
Okay, good. So my viewpoint on AI comes from Professor Valancourt. He wrote this really wonderful book called "Probably Approximately Correct." And that title's not a joke. That title is basically the current technical term for machine learnable. Okay. Now, the book, I do love this book. It basically serves as a feature length review article of the state of artificial intelligence. And he does wonderful things like pointing out that it should have just been called intelligence, not artificial intelligence. Okay. They gave it the wrong name. Anyway, the book goes straight to the jugular of human philosophy of our own existence, calling on an AI to develop to the point of being able to explain the algorithms that proteins use to create life. And that angle gives this feature-length review article a plot, so it's more fun to read. But that's where I get my perspective on AI. The book actually predates the popular buzz on AI. The book might be it might be 10 years old. I'm not sure. Anyway, so speaking firmly as a fan of Valancourt, he says the field of inorganic intelligence started with the field of numerical methods, which started with the publication of the FFT by Turkey and Cooley. I think it was in 1965, though I can't exactly remember. Anyway, so to the extent that AI is an extension of numerical methods, let's talk about numerical methods. There's an interesting thing there. So when Turkey and Cooley published that paper, it started a new field called numerical methods. The term numerical methods was not used before that. See, the thing is, Turkey and Cooley's, had that paper read like this, which is the way it did not read. It says, look, you guys better check this out. This thing is fast, but it's not as accurate. Well, then all the other people that worked in the field of computer computation would have said, when they realized that it's not as fast, they could have taken a big sigh of, oh my God, yes, okay, great. Your algorithm is very clever, but we've seen this before. Yes, you can. There are trades in life. You can compute something very fast, or you can have something very accurate. There's trades in life, and we have seen what you've done before. But that is not the way that paper read. That paper, the FFT isn't just fantastically is fantastically faster than prior methods of computing the Fourier transform. It's also fantastically more accurate. And that meant this was new. This is something we'd not seen before. And that was the field of numerical methods, which eventually became artificial intelligence. To the extent that SPICE is using AI, and I talked to the algorithm that it's using this brilliant combination of algorithms, it actually is AI, in my opinion, from an academic point of view. And you better believe it's AI. It solves circuits you can't solve by hand. It is intelligent. Okay. Now, that's not the nature of the current trade journal buzz on AI and machine learning that people like to talk about. And this is apparently driven by the fantastic successes that AI has had in human language. Okay. Now, I'm not seeing an application for that type of AI machine language in simulation, but my definition of simulation here is very narrow. It's the forward calculation of the behavior of a specific circuit. That, I think, is done well by the three numerical methods we started talking about, okay, of iteration, sparse matrix methods, and implicit integration. That is a solved problem. What AI should be doing, okay, the AI of the buzz is not simulating the circuit, but computing what circuit should be simulated. Okay, that would be, how AI of the current excitement would be. That's what we would be looking for if we're spending all our time looking for what AI is doing. And my opinion is that we're pretty far away from that. Okay, I don't. I think that I'm not. I have now. There might be. I'm sure there's people. I don't. I haven't seen anything that would give me any hope of that. Okay, maybe there are people that see it, but I have not experienced any reason to have hope in having a artificial intelligence decide what analog circuit I should be simulating. But where we do have an application, or where an application should be, is that if you have AI operate as an expert system, where organic intelligence, a human being, says, okay, I want, this amplifier here, and I want these gates here, and I want this logic here, and then the expert system takes care of how to instance out that amplifier and those gates. Okay, the idea would be so that an application engineer could design an integrated circuit without actually having to hire an IC designer. Okay, that I think is an idea whose time has come, but it's not quite here yet. I would look for that to happen in less than 10 years.
Great comment from your side. Even this was beyond what I was expecting. So we had a nice session today, and you are from Corvo, right? Did I spell it right? Corvo?
Yes, Corvo. Yes.
Corvo. So in our channel, the lot of audience are freshers. On behalf of them, I would like to ask if they want to have kind of jobs in Corvo. So what kind of profile they would be getting ready for?
Okay, well, first of all, Corvo is a great company. And I'm not doing that just because they have a habit of paying me. They are a great company. Okay, it has the stability and wealth of an S&P 500 company, but it doesn't have the dysfunctional organization of one. In large companies, it's too common for one MBA executive to make all the technical decisions and then pay a bunch of people to agree with him. Okay. Try not to waste your life like that. It's going to wear you down. Now, for Corvo, you go to corvo.com/careers, and that will show you the listing. And I can't really, yes, I am looking for someone. For someone fresh out of school, that's the place to look, and you should look at what they have. For me, I'm actually looking for my own replacement. Now, I do plan on working another 5 to 10 years, but life is finite. I should
Yes,
rephrase that. I
yes.
plan on working forever, but life is finite, and I think I think a responsible actuarial horizon to anticipate is 5 to 10 more years of actually coding like I code. Okay, so I'm looking for someone who would, who wants to become my replacement, and it's fairly demanding. It'd be like getting a whole new undergraduate degree. You'd have to temporarily set aside other aspirations to receive the knowledge that I do, and then we'd have to be convinced that you have the commitment to do that, to actually continue it on indefinitely, not just take the knowledge and run. So I am looking for my own replacement on that. But let me give you an answer of a little bit larger scope than getting a job at Qorvo. And it's because your question reminds me that I have a couple of times in my life been asked if I have any advice for young people. And I'd give an answer, and I realized that I gave the wrong answer. Okay, what I would do is I'd say, do something that you like.
Great.
Yeah, wrong. That's not good enough. There's too many actors waiting tables in Hollywood. Life is a struggle for survival. The right advice is to find something that you like, you're good at, and there's a market for. And if you do that, there's a better chance that you're going to feel like a responsible adult and that you'll be happy. Okay?
Correct.
Now, if you want to do something great, then you have to do something more than that. You have to up your game. And what you need to do is you need to combine knowledge from different fields to do something all new that no one's thought of before. Now, my attempt at that is, I try to combine physics, mathematics, electronic design, and computer science being both compiler and database theory, to write simulators. It's by combining all of these fields, you can make something actually new. And if you do combine them, then it's a lot easier. By combining knowledge from different fields, it's a lot easier to think of things that other people haven't thought of. An average guy can do it.
Great. So, well answered the question. And is there anything else you want to share apart from whatever I have asked or whatever discussed? Anything that you like to share? Because here the audience is a large audience here, and this video will get archived in the channel, and people will watch it maybe with timeline. So it will be there.
Well, I just Mirdal, I just appreciate your interest. I really do. Shukriya, Thunderbird, all that. That's all I really have. Thank you.
Yeah, and looking towards the viewers, I don't see any question from viewers in our comment box. So I would like to end the session here. I have asked for around an hour from Mike, and we are about to reach that. So thank you, Mike, for coming to the podcast and answering the lot of questions that I had, and probably this question may be there in mind of our viewers. And in addition, we got a lot of more informations and perspectives, or like a spectrum that we see through a prism, right? Different like VibGeors. So we had a wide spectrum of knowledge in today's discussion. Thank you, Mike, for giving that spectrum of knowledge. And so viewers don't have any questions, so I'll not bother Mike with any more questions. Thank you. Have a nice day, Mike. And bye today.
Bye-bye.
Bye for today.
Take care. Bye-bye.
Bye-bye.